Hello everyone, my name is Chi-Shih. I'm from University of California, Irvine. I'm working in Microsystems Lab, supervised by Professor Andrei Shkel. In this presentation, I will talk about a zero-velocity detector for self-contained inertial navigation system. Self-contained inertial navigation system is important for firefighters or first responders because they often operate in environments where GPS or GNSS signals are degraded. Although alternative signals such as LTE, Bluetooth, or Wi-Fi can be used for localization in indoor environments, in some extreme scenarios, those signals might not be available as well. In those scenarios, inertial navigation systems, or INS, are the only options. However, position estimated by INS drifts because IMU measurements are corrupted by noise and time-varying biases. For pedestrian navigation, we can mount IMU on a pedestrian foot and apply zero-velocity update algorithm or ZUPT to improve the navigation accuracy of inertial navigation system. The idea of ZUPT algorithm is based on the fact that when a pedestrian is walking, one gait cycle can be divided into a stance phase and a swing phase. The stance phase is the period when the foot is on the ground, and the swing phase is the period when the foot is traveling in the air. The ZUPT algorithm uses the knowledge that during the stance phase, the velocity of the foot is very close to zero. So during the stance phase, the algorithm feedbacks pseudo measurement of zero velocity to the output of INS and calibrate the IMU measurement. Inertial navigation system aided by ZUPT algorithm has been demonstrated to reduce the area of standalone INS. However, in the implementation of ZUPT algorithm, the critical component is stance phase detection. The accuracy of stance phase detection directly affects the navigation accuracy of the ZUPT-aided INS. Therefore, to have a high precision ZUPT-aided INS, it is important to have an accurate stance phase detector. One of the common ways to achieve stance phase detection is to use IMU already mounted on the foot. The measurement of foot mounting IMU can be used to detect stance phase because their profile in the stance phase is different from the profile in the swing phase. For example, the two plots you're seeing here are measurement of foot mounting IMU collected in one gait cycle. Left-hand side shows the 3-axis accelerometer readouts, and right-hand side shows the 3-axis gyroscope readouts. We can see that the measurement in the stance phase is very different from the measurement in the swing phase. To automatically detect a stance phase, several stance phase detector has been developed, and one of the detector is called Stance Hypothesis Optimal Detection Detector, or the Chi-Shih detector. The Chi-Shih detector relies only on IMU measurement, and the detection mechanism is based on this mathematical expression. This term highlighting in green uses information obtained from accelerometer readouts, and this term highlighting in blue uses information from the gyroscope readouts. The Chi-Shih detector defines the output of this expression as a likelihood statistic. The bottom plot you see here is a statistic computed based on the accelerometer readouts and gyroscope readouts shown in the upper two plots. To automatically detect the stance phase, the Chi-Shih detector compares a fixed threshold with the statistic. If the statistic is higher than the threshold, then the Chi-Shih detector determines a swing phase. If the statistic is lower, then the detector indicates a stance phase. Note that for different patterns of statistic, different values of threshold should be used to achieve the best detection performance and navigation results. The problem with stance phase detectors relying only on IMU measurement is that the profile of IMU measurement in different steps are distinct because foot dynamics is very complicated. For example, this is a Chi-Shih detector statistic collected in an indoor walking experiment. X-axis in this plot is the elapsed time, and Y-axis is the log of the statistic value. In the first 10 seconds of this experiment, the subject was standing still, so you see low values in the first 10 seconds in the plot. Each of the spikes in the plot correspond to the statistic in the step. The statistic I showed earlier correspond to this period of the experiment. The threshold indicated by the green line in this plot corresponds to the value that has the best detection performance. However, the same threshold for this step will be considered too high, and then for this step will be considered too low. Because of difference in statistic of every step, the performance of stance phase detector based only on IMU measurement and a fixed threshold does not yield the best detection result and navigation accuracy. To solve this problem, one way to do it is to develop threshold that varies in different scenarios. The other way is to include other non-inertial measurement and change the property of the detector statistic. Our approach is to include measurement from shoe-mounted downward-facing range sensor in stance phase detection. This is an experimental setup that we use to perform all experiments in the presentation. It is called the lab-on-shoe platform. The lab-on-shoe platform was previously developed in UCI Microsystems Lab to investigate sensor fusion solutions for inertial navigation system. For this presentation, we integrate an IMU and a downward-facing ultrasonic sensor on the lab-on-shoe. The ultrasonic sensor was placed 4 cm above the ground. The downward-facing ultrasonic sensor measures the height of the foot relative to the ground. This figure shows an example of the ultrasonic measurement collected during one gait cycle. This part of the measurement corresponds to the stance phase, and this part of the measurement corresponds to the swing phase. The ultrasonic measurement have a great advantage over IMU measurement in stance phase detection because the ultrasonic measurement always equals the same value during the stance phase. In this case, it's 4 cm. No matter what kind of activities are being performed, as long as the activity involves foot contacting the ground. For example, the right figure shows ultrasonic measurement obtained in another step. The measurements are always 4 cm during the two cases. So by combining ultrasonic and IMU measurement, we can have more consistency in the measurement profile in different steps. Our approach to combine the ultrasonic measurement and the IMU measurement is expressed in this equation. The term highlighted in blue correspond to the IMU measurement. They are inherited from the shoe detector. The orange term corresponds to the downward-facing ultrasonic measurement, which is the novelty of our approach. We named the new detector Ultrasound-Aided Stance Hypothesis Optimal Detection Detector, or the UA-shoe detector. To automatically identify the stance phase, we also compare statistic of the UA-shoe with a fixed threshold. If the statistic is higher than the threshold, it is the swing phase, otherwise stance phase. Coming back to the indoor walking experiment that we showed in previous slide and illustrate that the shoe detector statistic has different patterns in different steps. The bottom plot shows UA shoe statistic collected during the same experiment. We could observe that the statistic of UA shoe has more consistency in every step. The consistency can improve the performance of stance phase detection, and the improvement in stance phase detection will be beneficial to the navigation accuracy. To evaluate the UA shoe detectors in terms of navigation accuracy, we conducted 2 sets of experiments with the lab-on-shoe platform. Each set included 10 trials. In each of the trials, a pedestrian traveled in a straight line on a flat plane for 42 meters. In the first set of experiments, the pedestrian was walking, and in the second set, the pedestrian was running. For each experiment, we use ZUB-aided INS with different stance phase detector to estimate the navigation trajectory. The navigation performance of the different zero velocity detectors are evaluated based on the area of the estimated destination. Let's discuss the case of walking first. The left plot in the first row shows the 10 estimated destination when shoe detector was used, and the right plot shows the case of using our UA shoe detector. We use circular error probable, or CEP, to evaluate the navigation error. The CEP included at least 50% of the data. In the walking experiment, the CEP in the case of using Shih detector was 0.7 meters. In the case of using our UA-Shih detector, the CEP was 0.6. The experimental result of running experiments are shown in the two plots in the second row. In this experiment, the CEP of Shih detector is 1.7 meters. With aiding from ultrasonic measurement, our UA-Shih has a CEP of 0.7 meters. These experiments concluded that using our UA-Shih can improve the navigation accuracy of ZAP-80 INS when compared to the Shih detector. For conclusion, in this presentation, we try to improve the stance phase detection for self-contained pedestrian navigation. The problem with stance phase detection with only IMU measurement is that the measurement profile in every step are different, so it is challenging to use a single threshold to automatically detect all the steps. Our approach is to include a Shih-mounted downward-facing ultrasonic sensor for the stance phase detection. The inclusion of the ultrasonic sensor increases consistency of measurement profile in every step, which improve the detection performance and navigation results. Lastly, we conducted indoor navigation experiments to test the UA-Shih detector. The experimental result shows that the navigation accuracy of ZAP-80 INS can be improved when our UA-Shih detector is used. This work is funded by National Institute of Standards and Technology. Thank you for participating.